Section: Introduction. In this section, we discuss the importance of developing methods to automatically detect errors in responses from large language models, LLMs. We recognize the need for benchmarks that include clear error annotations to facilitate error detection analysis. To achieve this, tasks for collecting errors made by LLMs should be objective, realistic, and cover a wide range of errors. Tasks that involve subjectivity or do not have clear error labels are not suitable for benchmarking error detection methods. It is crucial that error detection benchmarks reflect errors similar to those encountered in real-world applications. Additionally, these benchmarks should encompass a variety of tasks to capture errors in diverse categories and challenge even strong LLMs to make mistakes. To address these requirements, we propose an approach that focuses on 4 evaluation criteria: reasoning correctness, instruction following, context faithfulness, and parameterized knowledge, to objectively evaluate errors in LLM responses. We introduce 3 tasks: math word problem generation, fine-grained fact verification, and answerability classification, designed to make LLMs introduce errors based on the 4 evaluation criteria. By eliminating subjectivity from the error annotation process, we ensure that these tasks are suitable for collecting mistakes in LLM responses for error detection benchmarks. Our benchmark, ReaLMistake, includes error annotations on responses from various LLMs, providing a comprehensive evaluation of error detection methods. Our analysis reveals that current error detection methods struggle to detect errors made by LLMs effectively. The performance varies among different tasks in ReaLMistake, highlighting the diverse properties of error detection tasks. We find that explanations provided by error detectors are often unreliable, and small differences in prompts can significantly impact error detection performance. Despite evaluating various methods to improve error detectors, we observe limited enhancements in error detection performance. In conclusion, ReaLMistake offers challenging and diverse error detection tasks, emphasizing the need for further research to enhance error detection methods for LLM responses. Previous evaluation methods such as ranking-based approaches are valuable for comparing LLM systems but may not be suitable for detecting errors in responses. Binary error detection is essential for automatically identifying and improving erroneous LLM outputs in real-world scenarios. Section Summary. In this section, we introduce the need for error detection methods in responses from large language models, LLMs, due to their increasing use in real-world applications. We highlight the importance of benchmarks with objective error annotations to evaluate error detection methods effectively, leading us to propose ReaLMistake, a benchmark that includes diverse errors made by LLMs across different tasks. Our analysis using ReaLMistake reveals challenges in error detection by LLMs, emphasizing the need for further research to enhance error detection performance in LLM responses. Section: Self-Improvement. In this section, we present our approach to self-improvement. We have observed that error detection is crucial, especially in enhancing LLM outputs based on feedback from LLMs. However, previous studies have mainly focused on refining outputs rather than analyzing the error detection process itself. Our ReaLMistake benchmark contains 900 instances with error annotations by experts on responses from GPT-40613 and Llama 270B across 3 tasks. These tasks aim to provide objective error labels in various error categories. One of the main challenges in creating evaluation benchmarks for error detection is collecting errors in LLM responses. Tasks used for this purpose should allow human annotators to provide objective error labels, introduce diverse real-world errors, and be challenging for LLMs while still feasible for humans to analyze. To address these requirements, we propose a strategy to design tasks that meet these criteria. Firstly, we focus on creating tasks that lead LLMs to make objective, realistic, and diverse errors. We identify 4 key criteria for evaluating errors in LLM responses: reasoning correctness, instruction following, context faithfulness, and parameterized knowledge. By designing tasks that align with these criteria, we ensure that errors introduced by LLMs can be objectively detected by humans. Secondly, we emphasize the importance of creating tasks that are challenging for LLMs but manageable for humans. Tasks that are too easy do not effectively test LLM capabilities, while tasks involving expert knowledge or extensive context may be too difficult for human annotators. To strike a balance, we design tasks that challenge LLMs in areas such as following requirements, comparing multiple texts, and detecting small mistakes in text. These tasks in our benchmark have proven to be effective in eliciting errors from LLMs while remaining accessible for analysis. Section Summary. In this section, we introduce the concept of self-improvement in error detection for language model (LLM) outputs. We present the ReaLMistake benchmark, which includes 900 instances of error annotations by experts on responses from GPT-40613 and Llama 270B, aiming to collect objective, diverse, and realistic errors in LLM responses for evaluation. Our strategy involves creating tasks challenging for LLMs but feasible for humans, focusing on criteria like reasoning correctness, instruction following, context faithfulness, and parameterized knowledge to ensure the tasks are both challenging and objectively evaluable. Section: Tasks. In this section, we present 3 challenging tasks that we designed for our benchmark. These tasks aim to capture a wide range of errors in LLM responses in an objective and realistic manner. By using 4 different criteria for evaluation, we ensure that the error annotation process is unbiased and diverse. Unlike previous tasks like chess or word sorting, our tasks focus on skills relevant to real-world LLM applications such as arithmetic reasoning and fact verification. The first task, MathGen, Math Word Problem Generation, involves creating math word problems that meet specific requirements. Models are evaluated based on their ability to follow instructions accurately and provide correct reasoning for the generated question. This task helps us identify mistakes made by LLMs without relying on complex mathematical concepts. The second task, FG-FACT-V, Fine-Grained Fact Verification, requires checking if each piece of information in a claim sentence is supported by evidence. This task emphasizes detailed explanations and evaluates the model's reasoning and faithfulness to context. We ensure objective evaluation by providing clear instructions to annotators. The third task, ANSELS, Answerability Classification, focuses on classifying the answerability of factual questions. Models must determine if questions contain factual errors and classify them as unanswerable. This task evaluates reasoning skills and knowledge about factual correctness. Our annotation process involved 14 faculty and graduate students who underwent training and verified each other's annotations. We filtered out cases involving grammar mistakes or subjective errors, ensuring that our tasks are evaluated objectively. Human agreement was high, with expert annotators achieving an average F1 score of 95.7 across the tasks, demonstrating consistent error labeling. Section Summary. In this section, we present 3 challenging tasks in our benchmark designed to capture diverse errors in LLM responses objectively. These tasks, involving arithmetic reasoning, fact verification, and answerability classification, aim to evaluate models based on reasoning correctness and context faithfulness, ensuring real-world applicability. Through a meticulous annotation process involving 14 participants and rigorous filtering, we achieved high human agreement in annotating errors, demonstrating the effectiveness of our objective evaluation criteria. Section: Error Detection Performance on ReaLMistake. In this section, we assess 12 different language models, LLMs, on their ability to detect errors in ReaLMistake. We aim to answer several questions. 1. How well can LLMs identify errors made by other LLMs? 2. Can LLM-based error detectors explain mistakes in LLM responses reliably? 3. How can we enhance LLM-based error detectors? And 4. Does ReaLMistake present challenging and varied error detection tasks? We present a table showing the error detection performance of the 12 LLMs using zero-shot prompts in ReaLMistake. The table displays the average performance on 4 different prompts. The random baseline predicts errors at the same rate as the error labels in each dataset. Human performance is also evaluated in each scenario. Furthermore, we explore the relationship between LMSYS LO rating and error detection performance on GPT-4 responses by the 12 LLMs in ReaLMistake. We observe that stronger LLMs can detect errors in GPT-4 responses with higher precision but lower recall. This trend is consistent when compared to performance on another task, MMLU. Additionally, we analyze the distribution of mistakes in explanations by LLM-based error detectors on responses from GPT-40613 in ReaLMistake. We find that open-source models introduce more errors compared to GPT-4 and Claude 3. The error detectors are evaluated based on their ability to classify responses as correct, with insufficient reasoning, wrong reasoning, or no reasoning. In our experiments, the LLM-based error detectors use the same prompts for all tasks, unlike criterion-specific detectors in previous studies. This approach allows for evaluation of criteria-independent detectors, enabled by the tasks in ReaLMistake that do not involve subjective criteria. We compare the error detection performance of the 12 LLMs in ReaLMistake to their LMSYS LO rating. The results show that while stronger models have higher precision in error detection, they struggle with lower recall. This highlights the challenges in LLM-based error detection. Overall, our findings suggest that error detection tasks in ReaLMistake are challenging even for strong LLMs, and the dataset offers diverse tasks with varying difficulties. Section Summary. In this section, we evaluate the error detection performance of 12 language models, LLMs, on ReaLMistake. We investigate how well LLMs can detect errors made by other LLMs, the reliability of explanations provided by LLM-based error detectors, ways to enhance LLM-based error detectors, and the complexity of error detection tasks in ReaLMistake. The results reveal that strong LLMs exhibit challenges in error detection, with high precision but low recall, and that ReaLMistake offers diverse error detection tasks with varying difficulties. Section. Explanations generated by LLM-based error detectors are not reliable. In this section, we instructed LLM-based error detectors to give explanations along with predicting binary error labels. We manually checked the explanations provided by error detectors like GPT-40125, Claude 3 Opus, and 3 open-source models, which showed good binary error detection performance. The distribution of mistakes in the explanations by the error detectors on responses from GPT-40613 is shown in the table. We found that GPT-40125 and Claude 3 Opus give explanations of decent quality but still make mistakes, especially on MathGen. The explanations by open-source models are often incorrect even when the binary predictions are right. They tend to make mistakes even for correct responses from GPT-40613, not just missing errors, leading to low precision. To enhance error detection performance, our analysis suggests that we need to make powerful LLMs more cautious about mistakes in their responses and enhance the reasoning ability of open-source models. We also looked into how small changes in prompts can affect error detection. By comparing the performances of LLM-based error detectors with 4 different prompts, we analyzed the impact of 2 changes: positional bias and wording bias. Positional bias refers to the order of error label options in the prompts. We found that placing the error option first led to higher recall, indicating that LLM-based error detectors prefer the first option. Wording bias compares 2 ways of asking to detect errors in the response, showing that small changes in prompts can influence error detection recall. However, these biases do not easily enhance error detectors' performance. Furthermore, we explored whether popular techniques used to improve LLMs could also enhance LLM-based error detection. We tested 3 common approaches: self-consistency with 5 samples, majority vote of binary error predictions by multiple models, and providing human written evaluation steps in prompts. Unfortunately, none of these methods improved error detection performance. This suggests that existing techniques for LLM-based evaluators are not enough to enhance LLM-based error detectors, making ReaLMistake a challenging task for error detection.